I'm delighted to be presenting our presentation. Oh, sorry. Well, first, I'm Harsha, not Rohan. Rohan couldn't be here, but I'm delighted to be presenting our paper on storage acceleration of retrieval augmented generation. LLMs have shown unprecedented capabilities, but the main question that industry is asking is how can enterprises extract grounded insights from the large corpus of data using foundation models? Well, the first option is to fine-tune an LLM. For fine-tuning, you take your enterprise's data, you pass it to a foundation model, and you use a lot of GPUs to fine-tune it. Because you need a lot of GPUs, this is an extremely expensive process. Moreover, once a response is generated by the fine-tuned LLM, the response is not grounded in specific references. In addition, what happens when you have new data? Do you simply fine-tune your model all over again? And finally, you still have hallucinations. The second option is large context LLMs. For large context LLMs, you take a large part of your enterprise's data, pass it to the LLM with the query as additional context to generate a response. But because your context is so large, you need a lot of GPUs, and again, this is very expensive. The other issue is LLMs have been shown to be bad at finding specific details in a large context that are most relevant to a query. And finally, you still have hallucinations. The third option is retrieval augmented generation, or RAG. For RAG, you have your query, which is then used to search an enterprise's database, which holds the enterprise's documents. The search process returns a few documents that are most relevant to the query and are used as additional context to generate a response. Now, because the search process does not use GPUs and just uses CPUs, it is cheap. Moreover, when a response is generated, it's now grounded in specific references. When you have new data that comes in, all you have to do is add it to your database, and in the next search iteration, it'll be part of the search process. And finally, RAGs have been shown to reduce hallucinations. RAGs are just one example of a Gen AI application that makes LLMs usable for enterprises. But RAGs also show that end-to-end Gen AI applications are not just LLMs. So I'm going to walk through a figure that shows retrieval augmented generation, specifically one incarnation of RAG, which is embedding-based RAG. In embedding-based RAG, you have your enterprise's documents, you embed them, and you hold these embeddings in storage. Now, in the first phase of RAG, called search and retrieval, when a query comes in, you embed the query. Once you've embedded the query, you then go to storage, fetch your first set of document embeddings. Then you do similarity checks between the document embeddings and your query embedding. Then you go back to storage, fetch your next set of document embeddings, and you keep repeating this process of fetching embeddings, doing computations, until you found the most or closest document embeddings to the query embedding. After you found the closest documents, you then go to storage, fetch the actual text representations of the documents, and use them to augment your query. And finally, once your query has been augmented, you can then use your LLM for generation. I want to emphasize here that the challenge was the interleaved storage accesses with computations we saw in the search and retrieval phase. One way of solving this is to store your entire database in DRAM. This is great if your database is small, but it's not a scalable solution. Moreover, it is not a cost-effective solution. In this graph, we're showing two RAG deployments, one where we store all the document embeddings in NVMe, and one where we store all the document embeddings in DRAM. Here, again, on the x-axis, we have the different RAG benchmarks, and on the y-axis, we have the dollar cost per query. What we see here is that when we use NVMe to store the embeddings, we have half the cost compared to storing all the embeddings in DRAM. This is especially important given the rising cost of compute for Gen AI applications. NVMe is great. It's scalable, it's cost-effective, but it has its own problems. So in this figure, we're showing the full runtime breakdown of retrieval augmented generation. On the x-axis, we have our different benchmarks for three different dataset sizes: 5 million documents, 50 million documents, and 500 million documents. On the y-axis, we have the latency breakdown. What we see is that no matter the benchmark, no matter the dataset size, the search and retrieval phase, when we use NVMe to store embeddings, dominates runtime. Even more important is that as we increase the number of documents, search and retrieval dominates more and more. This also shows that LLMs are not always the bottleneck. To understand what the bottleneck is, let's look at the search and retrieval runtime breakdown. So here, again, on the x-axis, we have our different benchmarks for three different dataset sizes, and on the y-axis, we have the latency breakdown. We see here that storage accesses, again, no matter the benchmark, no matter the dataset size, is dominating runtime. And we also see that as we increase the dataset size, storage retrieval dominates more and more. To resolve this issue, we did not just look to design another accelerator. Rather, we looked at the system as a whole and thought about how we can integrate an accelerator within the system to minimize these storage access overheads. What we landed on was placing the accelerator inside of storage with direct access to flash. To do this, we had to make sure the accelerator fit within the SSD's power budget and also involved minimal changes to the storage drive so it could function as a normal SSD as well. To understand the benefits of moving in storage, let's look at a commonly used algorithm for search and retrieval, specifically hierarchical navigable small worlds, or HNSW. Just a bit of context, the reason why we need this algorithm is because the entire point of retrieval augmented generation is that search process. Now we need to search over a large corpus of documents or document embeddings. We can't just brute force search the entire thing. We need an efficient algorithm to traverse over the embeddings or documents to find the most relevant documents to a query. HNSW is simply one example of this, and it's a graph-based approach. So the first step is to go to the root node of the graph and fetch the neighboring document embeddings. To fetch the document embeddings, you have to send an NVMe request, which then moves the embeddings over PCIe into memory. Now it's in memory, you can do your distance computations between the document embeddings and the query embedding. Based on these computations, you'll choose the document embedding closest to the query embedding and fetch that document embedding's associated neighbors. And again, for this, you have to traverse PCIe to get those embeddings from storage into memory. You do this over and over and over again until you found the closest documents to the query. By moving in storage, we can eliminate this PCIe traversal. More specifically, we give our accelerator direct access to flash to minimize the system overheads. So far, we've been talking about this problem in the context of a single storage drive, but it's very possible that our database exceeds the capacity of a single storage drive. In such situations, we need a way of handling this. Specifically for HNSW, what we did is we took the initial dataset, partitioned it, and for each partition, we created its own HNSW and stored it on its own storage drive. Storage is not the only issue. We also need to think about programmability. And the reason why we need to think about programmability is because there's a diverse range of search and retrieval algorithms. During our work, we came up with two classes, embedding-based retrieval and keyword-based retrieval. Embedding-based retrieval is what we've already been talking about, where you take your documents, embed them, store them, and search over them. Now, we specifically talked about one way of doing this, which is a graph-based approach. But there's also other ways of doing this. There's cluster-based approaches, there's tree-based approaches, and within these approaches, there's different implementations, and for each implementation, there's different ways of actually embedding the documents and embedding the queries. The second class of algorithms we call keyword-based retrieval. Keyword-based retrieval does not use embeddings. Rather, it looks at the actual words in your queries, in your documents, and looks at statistics like how often does this word appear in a document. To store this data, you could use a data structure like a posting list. And within posting lists, there's different implementations. And all of this is just to say that there's a bunch of different search and retrieval algorithms that we need to be able to support. To support this diversity of algorithms, we designed a metamorphic accelerator. Specifically, this accelerator is a shape-shifting architecture. Our accelerator takes on two views. In the first view, we decompose the columns of the accelerator into fully fledged vector processors. In the second view, we fuse these columns together to create a systolic array, except for the last row, which is a companion vector processor. Multi-vector mode is used for both embedding-based and keyword-based retrieval. Specifically, it's used for the distance computations between the document embeddings and the query embedding. Now, even within these distance computations, we need a level of reconfigurability because we have to support a bunch of different distance metrics, like the dot product, square L2, Manhattan, and BM25. Now, systolic mode is mainly used for embedding-based retrieval, specifically for the query embedding phase. Here we take the same PE microarchitecture and reconfigure it to just be a multiply and accumulate unit. And by doing so, we can support embedding models like BERT and GTR. On this slide, I'm showing our benchmarks, just some highlights. We looked at both keyword-based and embedding-based retrieval. We had a bunch of different distance metrics, and we had 4 different dataset sizes: 500,000, 5 million, 50 million, and 500 million documents. Here I'm just showing a few of the systems that we have in our paper. For the rest, I'm going to have to refer you to our actual paper, but the following slides, I'm going to talk about mainly 2 of these systems: CPU NVMe, which is our baseline, and RAGX, which is our system. For CPU NVMe, all of the document embeddings are held in NVMe, but the distance computations and graph traversal are all done on the CPU. RagX is our metamorphic accelerator, which is placed with direct access to flash. I want to emphasize here that for all of our systems, LLM generation was always done using 4 A100 GPUs. This graph shows our system's throughput improvement relative to the baseline, which is CPU and NVMe, but it also shows how our system performs as we increase the number of storage drives. This is specifically for 5 million documents. On the x-axis, we have our different RAG benchmarks, and on the y-axis, we have throughput improvement. What we see here is that we deliver a 2.3x improvement over the baseline, and this throughput improvement remains stable as we increase the number of storage drives. Now moving to 500 million documents, we see our throughput improvement jump to 5.7x. Now again, we see a stable throughput improvement as we increase the number of storage drive, and this all shows that our system actually scales as we increase the dataset size. To understand where these throughput improvements are coming from, let's look at a runtime breakdown of the full retrieval augmented generation pipeline. Here, we're specifically comparing the runtime breakdown of CPU and NVMe, the baseline, with our system RagX. On the x-axis, we again have our different benchmarks, and the y-axis is the latency breakdown. Looking at the average bars, we see that for CPU and NVMe, the bottleneck is clearly storage retrieval. But for our system, RagX, we drastically shrink this bottleneck, creating actually a new bottleneck, which is LLM generation, kind of showing a full circle moment. This shows that system and architecture co-design can lead to new innovations and new design ideas in different domains. Thank you all for listening to me talk. I think I've shown that end-to-end Gen AI applications are not just LLMs. Here we looked at one example of a Gen AI application, specifically RAG, and we saw that compute is not the main bottleneck. Not only did we go out and solve the actual bottleneck, which is storage retrieval, but we also had to consider programmability, which is the forte of this community. To provide programmability, we built the metamorphic accelerator, which can reconfigure its architecture at runtime to match whatever search and retrieval algorithm you want to run. And finally, I want to end our conversation on this one last idea. We believe that there's a new cycle of innovation that relies on system and architecture co-design to reduce cost and scale capabilities. We are very, very proud to say that we have built an open source infrastructure where we've been exploring this new cycle of innovation. It's public and available to everyone, and it's the Genesis project QR code shown here. We also have the artifact for this paper, which you can use to recreate some of our baselines as well as the results for our own system. Yeah, thank you guys for listening to me. I'd be happy to answer any questions.